Deep underground, in a hall the size of a football field, thousands of machines are spinning. Aluminum tubes turning just over 1,000 times a second, enriching uranium. On the control room screens, everything reads normal. Pressures, speeds, temperatures, all green. But the screens are lying. The machines are already tearing themselves apart, and for months, the operators won't realize why. This is the story of the first piece of software ever built to break things in the physical world. This is Stuxnet. To understand the attack, you have to understand the machine it attacked. To enrich uranium, you spin it. Uranium hexafluoride gas goes into a centrifuge. A tall, thin rotor turning at enormous speed. The heavier uranium drifts to the outer wall. The lighter, fissile part gathers toward the center. Do this once, and you barely move the needle. So you chain them together, the output of one feeding the next, into a cascade. At Natanz, each cascade held 164 centrifuges. Iran's workhorse was the IR-1, a fragile, first-generation design based on a decades-old blueprint. And the IR-1 has a problem. It breaks. Run it too fast, and the rotor, pushed near the speed of sound at its wall, cracks itself apart. So the speed has to be controlled, precisely, and held there. What makes this the ideal target is the thinness of that margin. The IR-1 already spun close to the limit of its aluminum rotor, so the attack never had to invent a destructive force. A deliberate overspeed of roughly a third was enough to push it to the edge of flying apart. It simply spent a safety margin Iran had little of to begin with. That control comes down to one component, the frequency converter. It sets the electrical frequency that drives the motor, which sets the rotor's speed. And every converter in the plant was commanded by an industrial computer most people have never heard of, a programmable logic controller, a PLC. At Natanz, they were made by Siemens. A PLC is not a laptop. It is a rugged little box with one job: read its sensors, run its logic, drive its outputs, thousands of times a second, for years without stopping. It is the muscle memory of the modern factory, and it was about to be turned against the very machines it was built to protect. And here is the engineering judgment that matters more than any single flaw. The controller is the one box where command and sense converge. It tells the converter how fast to spin, and it feeds the readings back up to the operators and the safety system. Compromise that single box, and you do not just get a foothold, you become the plant's ground truth. Here is the catch. Natanz was not on the internet. The control network was air-gapped, physically separated from the outside world. You could not simply hack in from a basement on the other side of the planet. So whoever built Stuxnet did not try to. They built a weapon that could cross the gap on its own. In safety terms, an air gap was never really a control. It is an administrative barrier, the weakest layer in the hierarchy, and it lapses the moment someone has to carry a project file across it on a USB stick. The mistake was not that it failed, it was treating physical separation as a defense, rather than one fallible layer among several. Stuxnet spread through Windows computers, and it carried 4 separate zero-day exploits. 0 days are unknown, unpatched flaws. They are rare and expensive, and most malware is lucky to have one. Stuxnet had 4. And to look trustworthy to Windows, it signed itself with digital certificates stolen from 2 real hardware companies. Its way across the air gap was the humblest thing imaginable: a USB stick. Plug an infected drive into a machine, and just viewing its contents was enough. No clicking. From there, it spread quietly, computers to computer, looking for one very specific thing: Because Stuxnet was not built to spread. It was built to wait. On almost every computer it ever infected, it did nothing at all. It was checking. Is this the Siemens software that programs these controllers? Are they the right model? Are the frequency converters the exact ones used to run enrichment centrifuges? If the answer was no, it stayed asleep. At Natanz, the answer was yes. What happened next is what makes Stuxnet different from every cyber attack before it. It did not steal data. It did not lock files for ransom. It reached through the PLC and into the physical world, and it did two things at once. The first thing was deception. Before doing any damage, Stuxnet sat on the controller and recorded the plant running normally, about 21 seconds of healthy sensor readings. Then, when the attack began, it played that recording back to the operators on a loop. That recording was only about 21 seconds long, and to a control engineer, that brevity is telling. A cascade in steady enrichment barely changes. Normal looks nearly flat for hours, so a short loop of flatline normal never drifts, never glitches, and never hands the operator a thread to pull. The engineers watched their screens. The screens showed normal speeds, normal pressures, everything green. The protective logic that should have tripped, running on the very controller Stuxnet had taken over, saw the same fake normal. Stuxnet even blocked the operators from changing settings mid-attack, in case they tried. The people in charge were staring at a recording of a healthy plant, while the real one was being destroyed behind it. The second thing was the sabotage itself. The centrifuges normally ran at just over 1,000 Hertz. Stuxnet waited until a converter was running in the exact range of an enrichment centrifuge, and then, over weeks, it struck in slow, deliberate bursts. According to the most detailed public analysis of its code, it pushed the converters toward 1410 Hertz. By analysts' estimates, that is near the edge of what the aluminum rotor can survive. It drove them there in short bursts. Then, weeks later, it slammed the same rotors down toward a near standstill before letting them recover. The two commands are not equal. The push toward 1410 Hertz was a brief, mild overspeed. The later crash toward a near standstill is the more brutal, because dragging a spinning rotor that fast through its critical resonances makes it whip and wobble itself apart with no overspeed needed at all. Spin a fragile rotor to the edge of its limit, then crash it, then do it again, weeks apart, just often enough to look like bad luck. The centrifuges cracked, they wobbled, failed, and had to be pulled out. And because the screens had been lying the whole time, no one could see a pattern. It just looked like the machines were breaking. There was a second layer of cover, and it was the target itself. The IR1 broke on its own, so extra failures read less like an attack than like the plant living up to its bad reputation. The uncomfortable lesson is that an attacker who picks a target that already fails on its own gets concealment for free. By the International Atomic Energy Agency's own cameras, something strange was recorded at Natanz across late 2009 and early 2010. Iran quietly dismantling and replacing around 1,000 centrifuges, roughly 6 entire cascades. The most cited analysis links that wave of breakage to Stuxnet. It is an estimate, drawn from inspection data, not a confession. But the timing is hard to ignore. For all its precision inside Natanz, Stuxnet got out. It spread beyond its target, onto ordinary computers around the world. And in June 2010, a small security company in Belarus flagged a strange sample that kept crashing machines. When researchers pulled it apart, they found something no one had seen before: malware that ignored the computer it lived on and went hunting for a specific industrial process. The security world realized it was looking at the first true cyber weapon, code written not to spy or to steal, but to physically destroy. The escape is usually told as the mistake that got Stuxnet caught. The more uncomfortable reading is that it exposed the limit of the whole surgical weapon idea. The payload was exquisitely targeted, and the worm even capped itself at 3 infections per USB key. Yet it still got out worldwide, because bolting a leash onto a self-spreading worm fights the carrier's whole reason to exist, and the carrier won. Who built it? No government has ever admitted it. But reporting, most prominently by the New York Times, described Stuxnet as part of a joint American and Israeli program, reportedly codenamed Olympic Games, begun under one president and accelerated under the next. Both countries have stayed silent. We state what was reported and what was proven. And those are not the same thing. So, what does a control room take away from this? 3 things. 1. An air gap is not a wall. Natanz was disconnected from the internet, and it was still reached through a USB stick and human hands. Physical separation slows an attacker down. It does not stop a determined one. 2. Trust your instruments less than you think. The deepest damage Stuxnet did was not to the centrifuges. It was to the operator's trust in their own screens. If your monitoring can be replayed back to you, then everything is normal means nothing. 3. Safety and control should never fully trust the same computer. When one box both runs the process and reports on it, compromising that box blinds you completely. Independent, hardwired protection that cannot be quietly overwritten is what stands between a bad day and a catastrophe. That third lesson has a precise engineering name: independent protection layers. Functional safety doctrine, codified in standards like IEC 61511, treats a real safeguard as separate in its sensor, its logic, and its final element. And by that test, Stuxnet did not defeat a protection layer. It exposed the absence of one, because the same controller it owned forged the readings, ran the logic, and drove the motors all at once. Stuxnet was, in a strange way, restrained. It targeted one plant and tried hard to spare everything else. The weapons that came after it were not always so careful. Next time, we look at the malware that crossed a line. Even Stuxnet did not. The first code ever written to attack the system whose only job is to keep people alive. If you want to understand the machines that run the world and the moments they fail, subscribe.